Dear student, in this lecture we'll learn a Verilog hardware description language. This is the part 1 video lecture. Myself, Dr. Asmuk P. Koringa, working as an assistant professor at Government Engineering College, Rajkot. Before going to what is a Verilog HDL, let's see where the Verilog HDL is used. So to design any VLSI IC, if we know the flow to design a VLSI chip, it starts with the system specifications. The system specification converted into the architectural design into the different block. Then architectural design have to convert into the logic design, where the Verilog or VHDL is used to convert the architecture design into a program. So it is converted our specification architecture design into a program which is nothing but the using the any hardware description language. So we have a two hardware description language used to convert the digital architecture into a program. One is the Verilog hardware description language and another is VHDL hardware description language. So what is a Verilog? It is a hardware description language to design a digital systems. So Verilog is used to describe a digital system architecture into a programming language. Two major HDL languages we have. One is Verilog hardware description language and another is VHDL. Verilog is easier to learn and use because its structure it is like the C language. So Verilog is close to C and C++. Comments line in a Verilog it is similar as we are using in a C and C++. Double slash for the single line comments, slash and star with the multiple line comments and with the star and slash. Verilog is a case sensitive language, right? And keywords are some reserved keywords, and all the reserved keywords written in a lower case. Like example, module, it is one of the reserved keyword in a Verilog. Case, initial, always, so all the keywords in a Verilog language written in a lower case, and Verilog is a case sensitive language. VHDL is not a case sensitive language, but Verilog is case sensitive language. The number it can understand the 4 numbering system. It can enter the data either in a decimal format, hexadecimal format, octal and the binary. String can enclosed with the 2 inverted comma. It's have the capital A to capital Z, small a to small z, and 0 to 9, underscore, dollar, all are the identifier in a Verilog language. And string are limited to 1024 character. So one string its size should be less than or equal to 1024 characters, should not be more than that. First character of identifier must not be a digit. First character of an identifier must not start with the digit. So any names should not be start with the digit. Now let's understand what is the numbering format in a Verilog. So format is, first of all, it is a size. We have to specify the number, how many, it's a binary bits required to represent, to implement the number. Then we have to specify the base format. It is given in a which format, and what is actual number. So size, it is not a compulsory, it is a optional. So if you not specified the size, it take the number, how many minimum binary bits required, it take the size of that number. So if you specified the size, it take that the size of the number. Base format. So base format, as we have discussed, the Verilog we can enter the data into the 4 binary number systems. One is the binary. For the binary, B it is used for the binary, D it is used for the decimal, O it is used for the octal, H is used for the hexadecimal, and if you not specified the base format, then by default it take the base format is decimal. Let's see some example given here. First number is 549. So in a 549, size of this number is not given. So it take the size as per the actual bit required, minimum actual binary bit required to represent 549 number. Now here the base format is also not given. So by default it you have to take in a decimal. So 549, it is a decimal number, and size of this is as per the minimum binary bit required to implement to represent the 549 decimal number. Another number here we can see the size is not given, but the base format is given H. So the number given in a hexadecimal number, and the number is 8FF. That means 8FF entering the number in a hexadecimal, and size it will take to represent the 8FF in hexadecimal. So it required each hexadecimal digit required the 4 bit. So it take the size here, it is a 12-bit number size. Third number here we can see again the size is not given, but the base format is given, the number entering in a octal format. So it is 765, take as an octal number. Fourth, if you see the size is given and the format is also given 11. So size here given is a 4 bits and the binary, but number is only the 11. So it add the 2 extra zeros before the 11, right, and it will make the 4-bit binary number 0011. For fifth number 3-B10X, so it represent the binary in 3 bits, so it take the 10X. Last is 5D3. So 5D3 means the size of the number is 5 and it is a decimal, given number is 3, but 3 can represent the 1 and 1, but here the size of number is 5, so we have to add the 3 extra 0, so it can represent 0, 0, 0 and 1, 1. Now let's see what is the program structure of an Verilog. So Verilog describes a system as a set of modules. Each module has an interface to other modules, right? And usually each module is put in a separate file, and top file level module that contains an instance of hardware module and test data. The module can be specified the 3 different architecture specification of a module. One is the behaviorally, structurally, and the data flow. So let's see what is the module and what is the program structure of a Verilog. So in a left hand side we can see the program structure, and right hand side it is given the example to implementation of a half adder, right? So let's see what is the program structure. So in program structure, start with the module. So this module, it is a keyword, right? And then we have to specify the module name, right? So module name, some have rules to specify the module name. Module name should not be any keyword, must not be any keyword. We cannot use a keyword to give the module name, right? And another rules for the module name, it must start with the alphabet. It should not start with any digit. Third rules for the module name is it must have a single word. Module name we have to specify in a single word. It should not have the space between the two words as a module name. So module name, some rules. In bracket we have to specify the port list. Now let's understand what is the port list. Suppose we are going to design a half header. So we know in a half header structure, so this is one chip we are designing for the half header. My drawing is not good. So in a half header we know it's have the one is XOR. So XOR gate. So two input of XOR, A and B are the input of half header. If we XOR it, A and B, it produces the sum bit of half header. So this is nothing but our sum bit of half header, sum. And if we ending the A and B, then it is nothing but our the carry bits of an half header. So if we end A and B, then it produces a carry bits. It produces a carry bit. So here we can see the logic to implement a half header. This is the half header diagram. Now what we have to write in a port list, right? So in a port list we have to write how many pins coming out from the chip. So here we are designing a half header, and it's have the 4 pin coming out from this box, which is box is nothing but the half header design, half header chip. So we have to write in a port list as a name of this pin, whatever the name we want to specify, A, comma B, comma sum, comma carry. Right, then we have to declare the portal declarations, right? So here we have specified the A, B, sum and carry, right? Sum and carry. Now out of this port, which port we want to use as an input? So this pin, 2 pin we want to use as an input port, right? And this 2 pin we want to use as an output port, right? So we have to declare it. So out of this A, B, sum and carry, we want to use A and B as an input. So mod is input A, comma B. And we want to use sum and carry as an output. So it can define as output sum, comma carry. And most of line in a Verilog and with the semicomma, and with semicomma. So here we can see most of line and with the semicomma except the AND module, right? Now third step is after the port declaration we have to declare the variable declarations. So what is the variable declaration? So inside the chip, if you want any jumper, suppose here from this we want any jumper inside the chip, if you want any jumper, that is declared as a variable declarations. In a Verilog, have two types of variable declaration. One is the reg and another is the wire. So wire is just forward the data, and reg is used to forward as well as the store the data. So here to implement the half header, we do not require any jumper, right? In which there is no any connection, there is only the single stage, not a multiple stage. So we do not require any variable, so not need to declare it. Last step is to description of behavior. So description of behavior is a internal description of the module, internal description of the chip, how the outputs and input have the logic relationship, that we have to describe, right? So here it's implemented using the data flow architecture modeling. So in data flow, assign sum, what we want to assign in sum. So we want assign in sum bit, it is a XORing of A and B. So we have to describe the behavior. So sum is equal to A XOR B. So this XCAP is a symbol to the bitwise XOR operations. And what we want to assign in a carry, So in carry, we want to assign the A and B. And this AND sign, it is used to denote AND operation. So it will perform A and B and it will assign to carry. Once our description of behavior, if we describe the detailed architecture in a language, then at the end we have to do the AND module. So you have to write the keyword. It is AND module. So it is very simple to write a Verilog code of any digital systems, right? So we remember structure of a Verilog code. It start with the module, then we have to specify the module name, and when we specify the module name, we should have to remember module name must start with the alphabet. It should not start with the number. Second things, module name we cannot give as a keyword name of the Verilog, so we can use other than that, and the module name must be a single word. After specifying the module name, in bracket we have to specify the port list and then port declarations. If we want to use any jumper, then we have to declare it. It is a variable declarations. And description of behavior, it can write into the three different architecture body, using the data flow behavior, data flow description, using data flow architecture description, using the behavior architecture description, and using the structural architecture description. We'll see in detail all the three architecture description in the next part. Let's see what is the variable in a Verilog. I have two types of variable. One is the range and the wire. Data object may have the value. So range and wire can understand four different types. One is the logic 0. It can understand the logic 0 or a logic 1 or unknown, and it's a high impedance. Register are initialized with the X at the start of simulations. So we remember when we not assign any value, it initialized with the unknowns. Any wire not connected to something has the value X. How to declare the memory in a Verilog? So if you want to declare a 1 kilobytes memory, then it can declare as a reg, then the width of memory. So here it is a byte, width is 1 byte, so 1 byte represented as 8 bit. So it is a big inverted comma, a big square bracket, it is 7:0, so it represents the width of the memory, right? And then the name of that register A, and this is the size of the memory, how many such words it is have. So it is 1023 to the 0, so it's have the 1024 such words, so it is a 1 kilobyte memory can declare. Now there are physical data types. So registers, it can store the value, and if you want to define it 8-bit registers, it have to be, we have to specify before the name of register reg, then we have to specify the width and then the name of that reg. If you not specify the width, it will take a 1-bit reg. So here X width is not specified, so it take X as a 1-bit reg. Similarly for the wire, right? So wire is just do not store the value. Register is store the value and the forward the data. Wire is just do not store any value. It represents the physical connection between the entities. Now similar to reg, wire is also, if you have the 8-bit wire, if you can represent the width and A and then wire. Types of Verilog coding. So Verilog can code in, as we have discussed, it can code in a 3 different architecture behavior description. First is the behavior architecture description. So in a behavior architecture description, it's a procedural codes similar to C programming. Little structure detail except the module interconnects. So here the code inside the always statement will run the sequentially. Another architecture is a data flow architecture behavior. So in a data flow architecture behavior, specific transfer of data between the registers. Some structural information is available, sometimes similar to the behavior, but in a data flow, all the statements run the concurrently. So we cannot use any conditional statement in a data flow architecture modeling. So it is widely used the data flow architecture modeling if our design we have the ready in terms of the Boolean equation where we knows how the data flow, what is the relation logical relation between the input and output in terms of the Boolean equation. At that time data flow to write the Verilog code in a data flow it's very easy. Last is the structural gate or switch level. So it is a interconnects of simple components and it's purely structural. So it is similar to the schematic when we prepare the circuit using any simulator, electronic circuit simulator, and how we are preparing the circuit using the symbol by inserting the symbol and connecting it and to make any circuit. So similar in a structural, it is just the connection of a different modules. So if our design is ready, we have different module is ready and we want to interface the different module. If you want to connect the different modules, then the structural architecture modeling, it's very easy to write the Verilog code. Now let's see what are the different operators. Suppose say the binary arithmetic operators. So here the symbols, it is similar to similar to the C language. So it is self-explanatory, not required to be explain it. Similarly, some have the relational operators to check the greater than or equal, less than or equal, equality, and the non-equality in any conditional operator. We can use this relational operators. Then they have the logical operators to check the logical negations, means inverting, to check the logical and the logical or. Then I have the bitwise operator to perform the operation to ending of the two bits or 2 bytes, right? So we can have the bitwise operator. This escape is bitwise negation, bitwise and bitwise or, bitwise XOR and bitwise XNOR. Other operators are the unary reduction operators. Means if you want to ending all the if we have the range of the 8-bit and if you want to end all the 8 bits and we want to check all the bits are 1 or not, so we can check by ending all the bits of the range, and if we produce the output is equal to 1, then we can say all the bits of that register are the 1, otherwise if produce output is 0. So it is have the unary reduction operators, means it's have the operand is only 1 operand. So suppose if you want to perform the AND, then you can write AND A, so it will perform the ending all the bit of A, right, in produce. Some have a concatenation operators. So if you want to take some bits from one register and some bits from the another registers, and if you want to combine, suppose some bit of some registers we want to put as an MSB and some are then LSB nibble or MSB nibble, and if you want to combine that, have the concatenation operator, and we have such concatenation operator. So here A of 0, it is a 0th bit of A, it will be the MSB bit of C, and then the rest of 1 to 7 bit of B register will work as an LSB bits of 1 to 7 of in a C registers. Then have some shift operators. So A less than 2 will shift the 2 bits right. Similarly, to shift the 2 bit left, we have the shift operators inside. Have the conditional operators. So here the conditional operator A equal to C greater than D question mark. So what will perform? So if this condition will true, when C is greater than D, then B plus C will assign into A. And when this condition will false, means C is not greater than D, then B minus 2 will assign into A, right? So it is a conditional statement it everything it is inside it, not need to write if this condition then this else this. So in a single statement it is have everything, right? Single statement it's have everything of the if else if. So A is equal to C greater than D means C, if this condition is true, then it assign the first value in a. If the condition is false, then it will assign the second value B minus 2 in a. Two procedure to construct. One is the initial statement and the always statement. So always statement used in a behavior architecture modeling. It make the program run the continuously in a loop. So initial it is execute only one time. So if you want to store the initial value in any variable, any port, we can store in a initial statements, and in always it run in a loop, right? So if you want to implement half header, then we can store here in initially we have to store the sum and carry 0 0, and then after depending on the A and B, carry and sum is it is reflecting, it will have the event as per the A and B. So this always statement run the continuously always at the rate A or B. That means if any change in A or change in B will run this program, and this run in program in a sequentially because it is in behavior. So it run this first this statement and then it will run these statements. In a Verilog have the few loop statements. So it is again it is similar to the C language. So it's have a repeat loop, while loop and for loop. Let's see what is the structure of a repeat loop. So repeat, it is a keyword, and then we have to specify the count. Then we have to specify the count, how many times we want to repeat this statement, how many times you want to execute the statements. So every time it decrement the count to 0. Once the count is 0, it will skip, it will come out from this loop. So here we want to add the sum plus 5 and we have to assign this to sum, and we want to repeat it to the 5 times, then we can write the count is equal to 5. So it will sum this repeat for the 5 times and comes automatically out from this repeat loop. Another loop is while loop. So in a while loop, inside this argument, it have some conditions when to run this program written inside the while loop. So whenever our count variable is less than 10, then it run the program between the end, begin and end of this inside the while loop. So we have to change the count value, right? And when the count value is less than 10, that many times it will continuously run the while statements, and once the count value is greater than 10, then it automatically come out from the while loop. Third is the for loops. So in a for loop, we know very well, for first it start with the what is the initial value of this count, 0, and conditions, and what should be the increment we want to set, right? So this increment here in a while loop, it is in inside the loop, inside the begin and end. Instead of that, in a for loop, it's taken as an that out in the conditional statement itself, begin and end. Now let's friends see how to implement. We have seen here the 2 input this half header we have seen. Let's see how to simulate using the Quartus II. Right, so once you open the Quartus II, you can see this is the you will see this window. Quartus II, it is a simulator tools which it is a CAD tools to design, and it is to convert the functional architecture. We can write the Verilog, so it convert that language into the synthesize it, and it produce the netlist for to design a physical design, right? Also we can verify our design. So it is an RTL register transfer level logic designing step. So what we have to do first is we have to go in a file new. Once you go in a new, it's have a different design file. So here we can see it is a design file. It's have a AHDL, block diagram, schematic design file, ADEF design file, state machine design file, system Verilog design file. So here we want to enter the code in terms of the Veriloghdl. So we want to enter our design in terms of the Verilog hardware description language. So we'll select the Veriloghdl. So once you select the Veriloghdl, it will open Verilog editor window. Here we can write the Verilog code. So we know that for the comments it's have a double slash. So here I written double slash, and this is the Verilog code for the half header. So let's write the Verilog code for the half header. Now it start with the module. Then we have to specify the module name. So let me specify the module name is half header. So it is satisfied all the conditions how to provide a module name, right? So here they start with the alphabets. It is a single word, and half header is not a keyword of the Verilog language. And what are the different port? So it's have a sum and carry. So it's have 4 ports. A, B are the inputs, sum and carry are the output. Now from the port, which port we want to use as an input? So we want to use A and B port as an input and single bit, and we want to use S and C as an output single bit. So it is not specified. Here we do not require any reg or wire for the interconnect. So directly we can start the logic. So in S, what we want to assign in S? So it is an XORing of A and B, XORing of A and B. And with what we want to assign in a carry. So we want to assign in a carry, it is a and B. So this is our logic description. Once the logic description is over, you have to write with the AND module. So this is simple a Verilog code for the half header. Now next step is we have to save this program with the extension .v. So let me save this program, right? It will ask where we want to save. Let me save here in my desktop, and let me make the folders. It's a half header, and we have to save this file with the module name. It is must, right? So we have to save this file, the module name, whatever the module name we have given. So here we have given the module name is half header. So we have to save this file with the half header, right? Half header. Once you will save this file, it will ask to want to create the project for this VHDL file. Yes, we want to create the project. So we have to click the yes. It is start the new project wizard in a Verilog to create the project. So it shows the directory where the project is saved and taken the project name as half header and our entity name is a half header. Right, this one file is added in this project. We do not want to add another files. Then in a which device we want to download our code. So whatever the board, whatever the FPGA chip in which we want to download this Verilog to make it a half header of any chip, then we have to select the chip in which we want to download our code, right? Then next step is to have any EDA tools. No, then finished. So it will comes in. You can see the project and the targeted device in a project navigator window. Right. Then after the entering the design in a Verilog and saving the file and creating the project, next step is to compile the project. So you can compile here. It is a one symbol for the compile, or go into the processing and start compilations. So once you compile, it will start some process. So first process is the analysis and synthesis. Means it will check the Verilog code is as per the syntax of Verilog or not. Then the synthesis. So it convert the Verilog into the netlist. So this code it converted into the netlist. Second step is the filter to perform the place and route. Right. So here we have selected the target device is Cyclone 2. So in that, whatever the hardware is form of this Verilog code, it were to put in the targeted device. Then in assembler, so we know assembler, it generate the programming file for to download on an FPGA chip, right? For if you select the target device is FPGA, then it generate .sof file, SRAM object file, and we know very well FPGA and architecture LUT, it nothing have the SRAM as a storage cell. So it generate a SRAM object file .sof. That file we have to download on a FPGA chip, and then after FPGA chip work as per the our design. It is a programmable chip. Then last step is the timing, classic timing analyzer. So it will generate the report for this design what will be the delay of input to a different output pins between the input and output pin. And in message window you can see the message of the design. So once it fully compile, it will give the summary, fully compilation summary. Next step is to verify the design. We have to be input the we have to take one input file. It is in a verification and debugging file types, which is the vector waveform file. Here we'll enter the our inputs and outputs. So right click in this place and insert the node and bus, find the node and bus and list out the node and bus from the entity and all the pins, list it. So here all A, B and C, select all and click it OK. So and provide the inputs. If you want to provide the inputs 1 and 0s and click and drag, and here it will be enabled a different logic. So let me provide the logic 1 for this, and let me provide the B as for the up to the end of simulations. Suppose if you want to provide a clock, then you can write the clock. After giving the input, let's save this file, right? And this file is half header, and save it. Then do the simulation. So before that, let's set the simulation in a setting mode. In mode simulator, instead of timing, let's set is the functional, right? In a timing simulation, we'll get the output with the delay. But in a functional simulation, it just the checking the logic, it is correct or not. So here we have to just check the logs, only the logic, as well the logic wise is giving at a half header logic or not. So we have set the simulator as a functional simulation, and for the functional simulation we required one more file need to be generated. It is a generate functional simulation netlist. So for that, go to in a processing and click on the generate functional simulation netlist. It will start to generate the functional simulation netlist. One is generate, it will give the message it is generated successfully. After that, start the simulation. So go to in a processing, and here you can see the symbol for the start the simulation. So click on it, it will start the simulation and it reflect the output as per the logic. So before the simulation, output was the X, don't care. And after the simulation, here we can see when our input is 0 1, then sum is equal to 1 and carry is equal to 0. Here we can see our input is 1 1. So carry is equal to 1 and sum is equal to 0. So as per the half header logic, we are getting a correct. So it is in this verification, it is called a pre-layout verifications, right? So this is what we have covered today. So we have in this video lecture, we have covered why the Verilog, what are the structure of a Verilog, what are the different architecture body of a Verilog, and how to simulate using the Quartus II. Hope you have liked this video and you have learned something new, right? Thank you for watching the video.